Assalamu alaikum everybody. I am Engineer Raja Farooq, Lecturer Mechanical Engineering Department, Bahauddin Sikriya University, Multan. And today we'll be studying chapter number 9, Welding, Bonding and Design of Permanent Joints from Shigley's Mechanical Engineering Design, 8th edition. In the previous slides, we learned about the weld symbol in detail, and now we are going to talk about the stress analysis of different weld types. Basically, we are going to talk about the stress analysis on a fillet weld and a groove weld or butt joint. Now, butt joint or groove weld can be applied with normal stress due to axial loading as well as in shear stress, whereas fillet weld can be used in transverse stress, parallel stress, where parallel and transverse stresses are basically combination of normal stress, different combinations of normal stress and shear stress, and we are going to talk in detail about these two in the coming slides. And bending load and torsional load can also be applied on the fillet weld. Now these are the topics which we are going to discuss in the coming section. Here we have a butt joint or groove weld under normal stress, which can be tensile or compressive, and from our knowledge of mechanics of material we know that stress is equal to F over A, where F is the applied load and A is the cross-sectional area of the weld, which is equal to H into L. H is the height of the weld and L is the width of this weld. However, you might have noticed that in the cross section we did not use this area of the reinforcement, or the reinforcement area was not used in the cross section of the weld, because this reinforcement might enhance the strength of the weld. However, it may also increase the stress concentration. So this reinforcement will increase the stress concentration, and that is why it is recommended to remove this reinforcement to avoid any stress concentration. Here is the summary of our last slide, and you can see a butt joint or groove weld being applied with a tension load. So if a butt joint or groove weld is in tension or compression, the formula will be F over A, where A is H into L and H is the throat of the weld. But throat does not include the extra reinforcement, because the extra reinforcement might add some strength for static loaded joints. However, reinforcement will also add extra stress concentration for fatigue loaded joints. So for fatigue loaded joints they need to be grounded off, and the throat is taken equal to the height of the parent metal. you can see that the height of the parent metal is equal to the throat of the weld. In this slide, we have a butt joint under shear stress. And the formula for shear stress is F over A. Once again, the cross-sectional area will be equal to H into L, where H is the throat of the weld and L is the width of the weld. We have learned about the butt joint or groove weld under normal stress and shear stress. Now we will be talking about the fillet weld. The shape of the fillet weld is of a right angle triangle, and if both the horizontal and the vertical sides, which are attached to the parent metal, are applied with shear stress, then that type of fillet weld is called parallel fillet weld. However, if one of the side is applied with normal stress and the other one with a shear stress of a fillet weld, then that type of a fillet weld is called a transverse fillet weld. Now, in this example, you can see that this force being applied on the fillet weld produces a normal stress on the vertical side, whereas this force produces a shear stress on side AB. So because we have a shear stress on one side and normal stress on the other side, that is why this type of fillet weld will be called transverse weld. Now coming to this example, you can see that the horizontal side as well as the vertical side of the fillet weld are being applied with shear stress. That is why this type of example will be considered as parallel fillet weld. So now we have a transverse fillet weld, as can be seen that one of its sides is being applied with a normal stress, whereas the other one is being applied with a shear stress. The leg size of this fillet weld is H and L is the width of this fillet weld. Now we are going to derive the formula for transverse fillet weld, and for that we are going to dissect this fillet weld at an angle theta, and we are going to isolate this section which has a normal stress on one leg being applied, and on the other side we have a shear force and a normal force being applied, whereas this one is the applied force F. Now from here we can say that the normal stress is going to be F n over TL, where T is this length and L is basically the width of this fillet weld. Similarly, the shear stress is going to be Fs over TL. However, the problem with these two formulae is that we do not have any concrete value for Fn, Fs or T, because if we change angle theta, the values for Fn, Fs and T will also be changed. That is why we need to have a derivation where we can convert Fn and Fs to force F, and similarly we need to convert this T to leg height H, because H is known as well as F is also known to us. So we are going to isolate this section as can be seen in this example, that we have divided this fillet weld at an angle theta, and we can see that Fs and Fn are being applied on this exposed section which has a thickness T, and this isolated section is being applied with a load F, and it has Fs and Fn. And to convert this Fs and Fn to F, we need to use our knowledge of summation of vectors. And in this we can see that the angle we have a right angle between Fs and Fn. Similarly, we have angle theta here, and we can say that this angle theta is between Fs and this vertical portion, and if there is an angle theta between two lines, then the perpendicular of those two lines also have the same angle theta between them. So if Fs and this vertical has angle theta, then Fn and this horizontal is going to have the same angle theta. So it means we are going to have this angle theta between Fn and F. So we can see from here that Fs is equal to F sine theta and Fn is equal to F cos theta. And next we are trying to find the relationship between T and H. To find that relationship, we firstly need to know that this length is equal to the leg size, which is H, as can be seen from here, that this side is equal to H, whereas this length is equal to T. And to find the relationship between T and H, we must need to use the sine law. In sine law, we need to know this angle, because this is opposite to H, and we would also need to know this angle which is opposite to T. Now it is very easy to find this angle, because we know that a fillet weld makes a right angle triangle, so this angle should be equal to 45. So we know that this angle is 45 degrees, and this angle is angle theta. If we draw a straight line here, then we know that we are going to have a 90 degree here, and we are going to have a 45 degrees here. Similarly, this side will also be equal to 90 degree, and this side would be 90 minus theta. So the angle opposite to H will be equal to 90 plus 45 minus theta, which is 135 minus theta. So using sine law, we can say that T over sine 45 is equal to H over sine 135 minus theta. As can be seen here. Next, we can expand this sine 135 minus theta by using the formula sine x cos theta minus sine theta cos x, and it will become sine 135. Sine 135 is equal to 1 over square root 2. Similarly, cos 135 becomes minus 1 over square root 2. So this will become under root or square root 2 divided by cos theta plus sine theta, because this negative sign along with this one is going to give us a positive sign. So finally we have this T over sine 45 is equal to square root 2 H over cos theta plus sine theta. This square root 2 is going to be cancelled out with this sine 45. So finally T is going to be H over cos theta plus sine theta. So here is a little summary of our conversions between Fs, F and Fn, similarly between T and H. So Fs is equal to F sine theta, Fn is equal to F cos theta, and T is equal to H over cos theta plus sine theta. Now we can plug these values in our formulae, which were normal stress is equal to Fn over T into L. Fn will be replaced with F sine theta. Similarly, T will be replaced with H over sine theta cos theta. Similarly, we are going to change this formula. Shear stress is equal to Fs over TL. So you can see that we have replaced this Fs and T with F and H, and we have this formula for shear stress as well as we have this normal stress formula. Next we are, because we have shear stress and normal stress being applied on a same plane, so we can use von Mises and we are going to get this formula, which is the von Mises for transverse fillet weld. And now as we have this angle theta available to us, so we can use this angle, and we are going to see that the largest von Mises stress occurred at angle 62.5, where von Mises stress was this one. Maximum shear stress was at 67.5 degrees, and the value for shear stress at that plane is 1.207 F over HL, and the value for normal stress at that plane is 0.5 F over HL. However, to find the maximum shear stress, we can also simplify it by using this formula shear stress is equal to F over 0.707 HL, which is 1.414 F over HL. The same formula goes for parallel fillet weld. Parallel fillet weld is the one where we have shear stress on both of the planes of a fillet weld. So The same formula goes for fillet weld as well as for finding the maximum shear stress on a transverse fillet weld. However, to find the maximum stress on a transverse fillet weld, we are going to use von Mises stress. We are now going to talk about fillet welds under combined loading. In a combined loading, we first have to examine the stresses. Then we will be talking about the strengths, and finally we will be comparing the strength with the stress. You see, we have two parent metals, and then there is a weld in between these two parent metals. We need to find the stress of all of these three parts: stress on parent metal 1, stress on parent metal 2, and similarly stress on the weld. Similarly, we will need to find the strength of our parent metal 1, strength of our parent metal 2, and similarly strength of the weld. And finally, we will be comparing these stresses with the strength. Stress and strength of them will be compared. So in a combined loading, firstly we need to find the primary shear stress due to external load. Then we will be working on the secondary shear stress due to external load, and in case of secondary shear stress, the external loads can be due to torsion or it can be due to bending. The formula for primary shear is equal to F over A, whereas the formula for a secondary shear can either be mr over J in case of torsional load, or it can be mc over I in case of bending load. Now, mostly students feel difficulty in finding the difference between a torsional load and a bending load. We are going to discuss about that in the coming slides. So once the stresses are known, next step is to find the strength of the parent metal. Similarly, we will be needing to find the strength of the weld. And finally, the strength and stress on parent metal will be compared. Similarly, the strength and stress of the weldment will be compared. And if the stresses are less than our strength, then it means our design is good to go. Well, one of the problems which students face in combined loading is to differentiate between a torsional load and a bending load. And to find whether a load is torsional or bending, we need to know the plane of moment as well as the plane of weld profile. So in this example, we have parent metal 1 attached to a parent metal 2 through a weld. And the profile of the weld is two lines which are in the top plane. For example, if this is our top plane, this one is our side plane, and this one is our left plane. Top, front or side, and this one is our left plane. Then the profile of the weld is in top plane. Now let's say if we apply the load on this parent metal 2, then this force is going to produce a moment in the top plane as well. So the moment as well as the profile of the weld are both in the same plane. You can see that if I apply this load here, this load is going to produce a moment in this plane, which is basically the top plane. So the plane of the weld, or the plane of the weld profile and the plane of the moment, both are same. So that is why this type of loading is called torsional load. So if the plane of the moment as well as the plane of the weld both are same, then we can say that it is a type of torsional load. Here we have the same example as the last one, but now we have this part in its side view. And the load is applied in this direction now. From this figure we know that the weld profile is in the top plane. So we are going to draw the weld profile here. However, the moment due to force or due to loading is in side plane. So we are going to draw the moment due to force in the side plane, and from here you can see that the moment and the weld profile are not in the same plane. So that is why this type of loading will be called bending load. So if we encounter any combined loading on a fillet weld, then we will firstly have to differentiate between torsional load and the bending load. And if the plane of moment and the plane of weld profile are same, then that type of loading is called torsional load, and if they are not same, then it will be a bending load. Now we have a fillet weld under torsional load, and when there is a fillet weld under torsional load or bending load, we firstly need to find the primary shear, then we are going to find the secondary shear, and once both of these shear are known, then we can find the overall effect of primary and secondary shear. The formula for primary shear is V or F over A, and to find the area of a weld we will need to look for table 9-1. It is available in your Shigley's Mechanical Engineering Design, chapter number 9, table number 1. Now weld profile can be different. The weld can only be on one side, then it is going to look something like this. If the weld profile is on two sides, then weld profile is going to look like this. If it is on three sides, it may look like this or may look like this. Both are same, or it can be all around our weld. So we will firstly have to find the correct weld profile. Once weld profile is known, then we can see what is the cross-sectional area of that weld profile, and the formula is given, all the formulae of some of the formulae of different weld profiles are given in table 9-1. Similarly, each of these welds have a centroid. For example, in this first profile, the centroid or the G point is going to be in the center. The G point for the second profile can be this, it can be at this point or it can be at this point. We will have to look for the profile and then we can find the G points. And once the G point is known, then we can find the distance of R from the G point. Similarly, the J can be found using this formula. J is equal to 0.707 HJU, where JU can again be calculated using the formula given in table 9-1. Once again, we will have to look for the relevant profile, and for that relevant profile we can look for the formula in table 9-1. So here we have table 9-1 giving us the torsional properties of fillet welds. If the weld profile is of a straight line, then the area or the throat area is 0.70 HD. The location of G can be found using X bar and Y bar, and JU is D cube over 12. JU is used to find J, where J is 0.707 HJU. Similarly, if the weld profile is like this, then this is going to be the throat area. The location of G can be found using X bar, Y bar, and this is going to be the formula for JU. And different profiles are available to us. You may use this table for all of these profiles. So here we have fillet weld under bending load, and just like the torsional load, we need to find the primary stress, the secondary stress, and then overall stress can be found using primary and secondary stress. The formula for primary is V over A, where A can be found using table 9-1. Table 9-2. 9-1 had the properties of torsional load, where 9-2 has the properties of a bending load. Similarly, for secondary shear stress, we have MC over I, where I can be found using this formula 0.707 HIU, and IU can again be found, can again be calculated using the formula from table 9-2. So here we have table 9-2, and it has bending properties for fillet welds, and just like a torsional load, it has weld profiles, different weld profiles. The first one is a single line profile. This is a double line profile. The third one again is a double line profile, but it is different than the second one. Then we have a 3-line profile, again a 3-side profile, and then we have a rectangular profile. And just like torsional load, we have formulae available for throat area, the location of G, and the unit second moment of area. All of these formulae are available, and based on the profile, we can use these formulae. So now we are going to solve example 9-1, and in example 9-1 we need to find the maximum stress in weld, and for that we will be needing to find the type of weld, whether it is a fillet weld or groove weld. We will also be needing to find the type of stress, for example whether it is normal stress, shear stress or combined loading. In this figure we can see that there are two parts being welded together. The first part has two plates and there is a shaft in between these two plates, and then there is a second part which is of a shape of an inverted U, and these two parts are welded together. You can see that we have a fillet weld on this side of leg 6 as well as a fillet weld of leg 6 on this right side. Now this one is our front view. We have the side view of same figure available to us as well, and in the side view we can see that the designer wants us to have a fillet weld of leg 6 on the left side as well as on the other side, which is our right side. And from front view we know that a weld is required at the top as well. So the shape of the weld is also an inverted U. So our weld shape is like this one, and you can see that the applied load is also in side view. We have also a 3D view or 3D model of this figure available to us. Okay, now we have the 3D model of our example 9-1, and here you can see the front view. This yellow part is our part 2 and this gray part is our part 1. You can see that our gray part has two plates and there is a shaft in between these two plates, and in the right view you can also see arrow of green color, and this represents the force being applied on the shaft of our part 1. And then there is weld on this side as well as on this side. Similarly, on the back side you can also see the welds, and you can also see the weld over here as well as over here. So we can say that there is a profile of weld on the right side as well as on the left side, and the profile on the right as well as on the left side both are same. So I hope you understand our 3D model. Now we go back towards solving our example. Now we know that there are two welds being applied in the front as well as on the back side of our parts. In the front as well as on the back side of our welds. But to ease our work we are going to use the front view. In the front view we can see this profile of the weld and the applied load. Now the applied load is 50 kilonewton, However, there are two profiles and we are only going to use one, so we are going to divide this applied load and we are only going to use 25 kilonewton, and we are only going to work on one of the profiles, either in the front or in the back. Now we are on example 9-1. It has three-sided weld being applied on two joints and 50 kilonewton force is going to be applied there. The profile of the weld is of an inverted U, and because we have two same profiles, so we can use 25 kilonewton on one profile instead of 50 kilonewton on two profiles, just for simplicity purpose. Now we can see that this 25 kilonewton is going to produce a moment M, and this moment is on the same plane in which our weld profile resides. Because moment and weld profile are in the same plane, so we can say that this weld is going to be applied with torsional stress. And in torsional stress, we know that we need to find primary shear as well as secondary shear. And once primary and secondary shear are known, then we are going to find the overall effect of primary and secondary shear. Because we have a 2D problem here, the formula for overall stress is going to be primary X plus secondary stress plus primary on Y plus secondary on Y whole square whole under root. So we need to find primary stress, secondary stress, and the maximum or overall stress. And this overall stress is going to give us our required maximum stress being applied on the part. As in this question, we need to find the maximum stress being applied on the weld. So we are going to find this combined effect of the stress, and that is how we are going to find the maximum stress. So let's start off with finding the primary stress. So the formula for primary stress is equal to F over A, where F is 25 kilonewton because we are only using one of the two profiles, so it is going to be 25 kilonewton, and this area is throat area, and to find this area we will have to seek help from table 9-1. We will be looking for the weld profile, and once we get our weld profile we can find the throat area. We have only single-sided weld available in our first type. In the second type we have double-sided weld. In third type we also have double-sided weld. In fourth type we have a three-sided weld, but the orientation of this three-sided weld is not same as our weld. However, if we turn it counterclockwise at a 90 degree, then we can get our same weld. Now if we rotate it at 90 degrees, then we are going to get the profile of our weld. And now we can see that this point is called G point, which is the centroid of this weld. This side is B and this side is D, as you can see in this fourth type of weld. Similarly, the distance between top side and G is called X bar, and the distance of G from the right side is Y bar. But we need to find the formula for throat area, and we can see that the throat area is provided here. The formula for throat area is provided, and that formula is A is equal to 0.707 H 2B plus D, where B in our case is the height, D is the width of the weld, whereas H is the leg size of the weld. And we know from our problem that the leg size is 6, the height is 56, and the width is 190. We are going to plug these values in, and we are going to find the value for our throat area. 0.707, leg size is 6, height is 56 plus width 190. So throat area comes out to be 1280 millimeter squares. We are going to plug this value in our formula. 1280 millimeter square, and primary stress is 19.5 megapascals. So now we know our primary stress is equal to 19.5 megapascals. Now we are going to find the secondary stress, and the formula for secondary stress is equal to MR over J. Secondary stress is equal to MR over J. So let's find out the value for moment. M is equal to force times distance. We know the value for force, 25 kilonewton, but we do not know the value for the distance. However, we know the profile of our weld, and we also know that its centroid is at point G, and force is applied at a distance 100 mm from the weld. As mentioned in our question. But this is not the total distance to find moment, because the total distance is between the point of application and the centroid. This is going to be the total distance. So we also need to find the distance between the upper surface and the centroid of the weld, which from table 9-1 we know is x bar, and the formula for x bar is equal to b square over 2b plus d. X bar is equal to b square over 2b plus d, and b square is 56 square over 2 into 56 plus d 190. So this comes out to be 10.4 mm. So the total length is equal to 100 plus 10.4 mm. So moment comes out to be 25 kilonewton into 110.4, and the value of moment is 2760 Newton meter. Next we need to find the value of R. Now R is the distance between centroid and the point of interest. For example, if this is our centroid G and we want to find the value of stress at this point, let's say we are going to call this point A, then R is going to be this straight line distance between G and A, and we are going to call it RA. And to find RA, we are going to make a right angle triangle here, where this side is 190 divided by 2, which is 95, and this side is 56 minus x bar, which is 10.4. So 56 minus 10.4 is going to give us 45.6. So working on this right angle triangle can give us the value between G and A. This is our point G and this is our point A. This perpendicular is 45.6 and base is 95. So we can easily compute the value for RA is equal to 105 millimeter. But remember that we wanted to find the maximum stress. And we do not know if the maximum stress is going to be at point A or at some other point. So we are going to take these 4 points, these 4 edges or corners. We are going to name these 4 points and we are going to compute the value for RA, RB, RC and RD respectively for all of these points. And we know that RA is basically equal to RB. Similarly, RC and RD can also be computed, and their value will come out to be 95.6 millimeters. So now we have computed the value for M, for R, and lastly we need to find the value for J. Now J is equal to 0.707 HJU, and to calculate the value of JU we will once again need the help of table 9-1, and we can see in table 9-1 that the formula for JU is provided to us, and we can use this formula to compute the value of JU. And you can see the only variables in this formula are either B or D, so we can easily plug the values of these variables and can find the value of JU. So now we know the formula of JU, we can easily compute the value of J. 707 H leg size 6 into the value of JU, which is 8 into 56 cube plus 6 into 56 into 190 square plus 190 cube whole divided by 12 minus 56 raised to the power 4 divided by 2 into 56 plus 190. And the value of J comes out to be 7.07 into 10 raised to power 6 millimeter raised to power 4. So now we know the value for M, value for M, R and J are known, so we can find the value for secondary shear stress. However, we need to find the secondary shear stress at point A, B, C and D, and because RA is equal to RB and all the other variables are also equal, so the secondary shear stress at RA will be equal to RB. Similarly, the secondary shear stress at C will be equal to D. So secondary shear stress at point A is equal to secondary shear stress at point B is equal to M, which is 2760 Newton meter. 2760 Newton meter into RA or RB, which is 105 Newton meter, 105 millimeter, and the value of J, which is 7.07 into 10 raised to power 6 millimeter raised to power 4. So the value for secondary shear stress at point A and B is 41 megapascal. Similarly, secondary shear stress at C and secondary shear stress at D are equal, 2760 Newton meter into RB or RC, which is 95.6 millimeter. 95.6 millimeter divided by the value of J 7.07 into 10 raised to power 6 millimeter raised to power 4. So the secondary shear stress comes out to be 37.3 megapascals. So now we know the value of primary shear stress, which is 19.5 megapascals. Similarly, we know the value for secondary shear stress at A is equal to secondary shear stress at B is equal to 41 megapascals, and secondary shear stress at C is equal to secondary shear stress at D is equal to 37.3 megapascals. So now we are going to find the maximum stress, and we know its formula, which is this. Now let us find the orientation of primary and secondary shear, so we may plug in the values for these variables. So now let us find the orientation of primary and secondary shear. We know the profile of the weld, and we also know the applied load is 25 kilonewtons. If force is from left to right, the primary shear is going to be from right to left. So in this case we only have primary X and we do not have the value for primary Y. That is why we can eliminate it. Now let's find out the orientation of our secondary stress at point A, B, C and D. And to find the orientation, we will also be needing RA, RB, RC and RD. We know that the applied load is trying to move RA, RB, RC and RD in clockwise direction. So the secondary shear stress will try to move this in counterclockwise direction. So secondary shear at A will try to rotate RA in counterclockwise direction, and it is going to make an angle 90 with RA. Similarly, secondary shear at C will also try to rotate RC in counterclockwise direction, and it again is going to make an angle 90. Same goes for secondary shear at D and secondary shear at B. And now we know that the secondary shear do not have any orientation in X or Y, so we are going to find the X and Y component of secondary shear stress at A, B, C and D. So if this is our G point and this is our A point and this is our secondary shear stress, making some angle with its X and Y component. Now we will try to find the X component of secondary shear stress at A point and Y component of secondary shear stress at A point. For that we need to find an angle between secondary shear stress and X component or the Y component, and for that we are going to use this RA between G and A. We know that this length is 95 and this length is 45.6. So we can use these lengths to work out our angle. And we are going to do the same for our rest of the secondary shears. Once all of these are known, then we can find the overall stress at point A and at point B because they are going to be same. So we are going to write the X component 19.5 X component of primary stress plus or minus X component of secondary stress, and we know that this X component, these two X components are in different directions, so that is why we will have to plug minus here. 19.5 minus secondary shear X component sine 25.64 plus X component, Y component of our secondary shear 41 cos 25.64. So our shear stress at A and shear stress at B comes out to be 37 megapascal. Similarly, we can find this shear stress at C and D. Sorry, we need to plug square here. So primary X component of primary stress minus or plus, but here for C and D we know that the X component of secondary and primary both are in the same direction, so we are going to plug plus here. 37.3 sine 6.25 whole square plus 37.3 cos 6.25 whole square. And shear stress at C and D are 44 megapascal. So our maximum stress comes out to be 1 44 megapascal. That's all for our example 9-1. Next we are going to work on the strength of our welds.